Conservation of momentum in an inelastic collision. In this video we'll take a look at what conservation of momentum is, what momentum is for that matter, and then we will solve a simple problem involving an inelastic collision where we will apply conservation of momentum to help us solve that problem. Now if you're watching this video, you probably already know what momentum is, but we can think of it informally as mass in motion. It considers both an object's mass and its velocity. In fact, you obtain momentum by multiplying an object's mass, measured in kilograms, times its velocity, measured in meters per second. And so the units for momentum are kilograms, meters per second. To represent momentum, we use, for some reason, a small p. And yes, see that little arrow over the p? It is a vector, which means momentum can be positive or negative. If the object is moving to the right, it has positive velocity and therefore positive momentum. If it's moving to the left along a number line, let's say, it has negative velocity and therefore negative momentum. Here's a simple example of a momentum calculation. We have a bright green ball moving to the right. It has a mass of half a kilogram, velocity of 20 meters per second. And so we multiply those two things together to get its momentum equal to 10 kilograms meters per second. Now let's consider another object, this time a bullet, much smaller mass, moving to the left, negative velocity. So to get its momentum, we multiply its mass and its velocity, and we get minus 10 kilogram meters per second. Same magnitude as the ball, but opposite in sign because it is moving to the left. And notice how we can get equivalent momentums by different combinations of mass and velocity. Large mass, small velocity can have the same magnitude of momentum as something with a small mass and a much larger speed. In this case, the velocity is negative, and so the momentum of this object is also negative. So again, momentum is the product of mass and velocity. It can be positive or negative. To the right, we call positive. To the left, negative. Momentum has an important property in that it is conserved in an isolated system. So we need to talk about what do those words mean. Well, conserved in this instance means that it is constant. The total amount of momentum is not going to change. The second word we threw in there was system. Conservation of momentum applies in an isolated system. That is a system where there's no forces from outside the system that are acting on the system. Again, then the total amount of momentum in this system before and after some sort of interaction is going to be the same. And these interactions can be collisions or even explosions. Here are the type of interactions where we will typically apply conservation of momentum. The inelastic collision, that's what we saw in the very beginning of this video, where two carts collided and stuck together. Elastic means bouncy, so in this case they didn't bounce off, so inelastic. You can also have an elastic collision where two things collide and do bounce off each other. You've probably ridden bumper carts at the fair. And finally, we can have an explosion where we start with one object. There's some sort of internal force which splits the object into two separate objects going opposite directions. Again, we term that an explosion. This template illustrates our basic problem-solving strategy for using conservation of momentum to solve problems involving collisions and explosions. The principle that we're going to use is the conservation of momentum. We're going to look at the total amount of momentum before the collision or explosion, and then we're going to look at the total momentum after the collision or explosion, and those two things are going to be equal, and that's going to allow us to solve for any unknown quantities in the problem. Okay, it's time to look at conservation of momentum in real life. Let's roll it.
So here we are. We have a beautiful day out on the Sunshine Coast. Got this beautiful... Oh no!
We are going to turn that video, that cat video, into our own conservation of momentum problem. Here's what we got. We got a kitty saying its mass was 3 kilograms. It was moving at a velocity of 4 meters per second. And it is going to collide with a surfboard, mass of 9 kilograms. The surfboard's just sitting there, so it's got 0 velocity. And the cat and the surfboard stick together, so it's an inelastic collision. They basically become one object. Their mass now is a combined 9 plus 3, 12 kilograms. We're trying to figure out what's the velocity of that combined kitty plus surfboard. Remember that conservation of momentum only applies in an isolated system. And we've defined our system as the kitty and the surfboard. They collide inelastically, and over here we've got them together. And we are specifically excluding consideration of the friction between the water and the surfboard. Sure, the water probably slows down the surfboard to some degree, but it's going to make our problem-solving approach much simpler to exclude that low-friction interaction from our analysis. Okay, here's our basic template again. We've got the problem written out here at the top. And again, we have divided our analysis into 2 sections. What is the situation before the collision? What is the situation after the collision? Somewhere in the middle here is the actual collision. I strongly encourage you to draw the problem. And don't be self-conscious about your drawing skills or lack of same. I've drawn here the kitty and the surfboard. That's our system. This is before the collision. And then over here I've got kitty hanging out on the surfboard, cruising across the swimming pool. Before and after. Here is what we are trying to figure out, the final velocity of the combined cat plus surfboard system. Now I think there's a typo here. This, instead of saying 9, that should actually be, right, 12 kilograms, the combined mass of the kitty plus surfboard. And we've got this nicely laid out here on our template. We're going to look at momentum before and momentum after the collision. We're now going to calculate the total momentum of our system prior to the collision. And to do that, we look at each object, the kitty and the surfboard, individually because they are not connected at that point. First of all, we get the total momentum of the kitty, multiplying its mass times its velocity. 3 kilograms times 4 meters per second, we get 12 kilogram meters per second. Now for the surfboard, that's a pretty easy calculation since it has a velocity of 0. Its momentum is also 0. To get the total momentum before the collision, we add the momentum of the kitty and the surfboard. 12 plus 0, we get 12 kilogram meters per second. Very important now, this momentum that we calculated for the system before the collision, we can transfer over to the other side because momentum is conserved. Now here's the final step of the problem. We know that the total momentum of the system is 12 kilogram meters per second. And the mass of the system, well, we've got the kitty and the surfboard together. Their combined mass is 12 kilograms. So we've got that information here. Mass, 12 kilograms. We know that momentum is the product of mass and velocity. So we're going to substitute in here 12 for momentum, 12 for mass, our variable v for velocity. Divide each side by the mass of 12 kilograms. This one works out pretty easily, you'd have to say. And you're going to get that the velocity is the momentum divided by the mass, and you're going to get 1 meter per second for the combined kitty and surfboard. You can use the same principle of conservation of momentum to solve all sorts of problems involving collisions and explosions. Hey, thanks for watching. Hope you enjoyed this video, maybe learned a thing or two. Up with the Hatters.